Shanawaz. In this lecture, we are going to introduce the notion of a category. So, we define a category via directed graphs. Let us consider the vertices. This vertex A, this vertex B, this vertex C, and let us note this vertex by D. So these vertices are called the objects of the category. So, and between these objects we have these arrows. Now they are called the morphism. Suppose we have F from A to B, an arrow say G from B to C, and an arrow from C to D. So let us denote this arrow by H. So these arrows are called the morphisms. So that is all what is needed to define a category. So let us define this category. So category C, a category C consists of the following ingredients. So the first ingredient is it consists a class which we denote by obj of C. This class is called the objects of the category. Called objects of the category. Of the category. And for each pair, say AB, in this class obj of C, we have a set let us note this set by home of AB. Now this set home of AB, this contains a set of contains all morphisms from the object A to the object B, whose elements are called these elements are called morphisms or arrows from A to B. Morphisms or arrows from A to B. And if we consider any ordered triplet, for an ordered triplet, A, B and C of objects, so there is a composition, composition law, that is composition law. So I mean, if home of AB times home of BC to home of AC, denoted by, so if we have this F and G here, it goes to G composite with F. So what this means, so if we first go from A to B via F and from B to C via G, it is same as to go from A to C via this composition map. So note here, this F is in this is an arrow from A to B, so it belongs to home AB, and this G, this is an arrow from B to C, so this G is in home BC. So it takes an element F in home AB, so this is home AB, it takes F here and an element here, that is home BC, so this is G. Now it maps this pair FG to an arrow from A to C. Now there is an arrow from A to C, that is the composition map, so that is, so this G or G composite F is in home AC. And for each object, suppose for every object A in C, for every object A in the category C, we have the identity morphism, i.e. we have IA, which is in home AA, so this is in home AA. This is in home AA. That is, for each object A we have a morphism from A to A, that is IA. Similarly, we have a morphism from D to D, that is ID. Same is the case with C and with B. So here is IB. Now these four ingredients, they are subject to the natural conditions. So these ingredients are subject to the following natural properties. That is, so first natural property is the associativity axiom. Associativity axiom. So if we are given morphisms, say an arrow from A to B, similarly an arrow from B to C, and an arrow from say C to D, then this composition is valid, this condition is valid. So this is A here, this is B, this is C, this is D. So this is the morphism F, this is G, this is H. So obviously these two compositions are from A to D. So if we, so one can see over here, so if we go from B to C, then C to D, it is same as to go from B to D. So this is the composition map H composed with G. Now to go from A to D, there are two ways. First, we can take this route G composed with F, and then this H. So this is first take this route G of F and then H. Now there is another route. First go from A to B via F, and then take the route from B to D, which is by HG. So we can reach from A to D via these two routes. So there should be no distinction in these two routes. So either you take this route or this route. So we have this route here, this is the route H. So first we are going via this map here and then compose it with F, or you take this route here. This is first you go via F and then go via H or G. So these two things should coincide. Now there is one more axiom, that is the axiom of identity, or the identity axiom. So we have the identity axiom. So given morphism, say, so this is morphism. So given a morphism, say F in home AB, and yeah, or let us write here, given morphisms F in home AB and an arrow from say B to C. So we have these three objects here, A, B and C. So this is the arrow F here. So this is arrow F here and this is arrow G here, and On A we have this identity morphism IA. Here we have this object B, we have the identity morphism IB, and on C we have the identity morphism IC. So for this axiom we will focus on a particular object, say B. So at B we have an arrow which lands in B and an arrow which comes out of B. So if we first take this F here, so F takes us from A to B, then we at B we operate this morphism here, so we end up at B. So this is same as the morphism F, and now instead of F if we first operate this morphism here, that is I and B, and go to C via G. So this is same as going from B to C, and this is same as going from A to B. This is same as going from B to C. So this is the axiom of associativity. Now one can note here, this is a class of objects, and here we take this set, but more generally this is a class as well. So if we make some little definitions here, so first that is called a locally small category. So if we take this home AB as a set, so if we take this as a set, then the category here is the locally small category. So in this series, in this lecture, in this course, we are dealing with the locally small categories because we are taking this as a set, but more generally it's a class home AB. So that is called a locally small category. Then we have this category called the small category. So in this category we take this class object of C just as a set. So if we consider this just a set, then this is called this category is called the small category. Now let us do some examples. So first of all, we'll consider this category of sets. So let us note this S with the fancy letter S. So this is the category of sets. So in this category the objects are sets and the morphisms are just the maps between the sets. So this is a very important example of category. You know, there this is not there, I mean this is an important category in the sense because had we have taken this C to be the set of set, then there is something called the set of all sets, and that will lead us to the Russell's paradox. So to take care of Russell's paradox, we need the category of sets. So we don't talk about sets here. So in this category, the objects are the sets, and the morphisms, they are just the maps between sets. So in Russell's paradox, this is about sets. We don't have a set of all sets, because that won't make any sense. Second is the category of groups. So this is the category of groups. So here the objects are, they are just the groups, and the morphisms here are group homomorphisms. And then we have the category of rings. So similarly, objects here are rings, and morphisms are ring homomorphisms. And then we have the category of modules. So objects are R modules, where R is the underlying ring. So the objects are R modules, and the morphisms are R module homomorphisms. And then we have the category of topological spaces. So let us denote this is the category of topological spaces. So objects here are, they are topological spaces, and the morphisms are continuous maps. Sorry, I mean the category here is the objects are just open sets, because in a topological space we define continuous maps from open sets to open sets. So open sets, and then we have the category of topological spaces, but that is a different category, in which open objects are just open sets, but the morphisms are homotopic maps. So let us note this category by H top. So objects here are again open sets, but the maps here are, I mean morphisms, they are the homotopic maps. And let us define one more category, say the category of, say, matrices. So in this category the objects are natural numbers. Natural numbers, and the maps are matrices, i.e. the linear transformations. So morphisms are matrices which are just linear transformations. So one can view here, so we have, say, there's an arrow from 3 to 4. One can view this arrow as a morphism from a 3-dimensional vector space V3 to a 4-dimensional vector space V4. So the morphism here is a matrix of order 4 cross 3. Now there are other examples of categories. For example, let us mention this category here. This is, so let us make this category as a separate example. So one can view a partially ordered set. So a poset, by a poset we mean a set on which we have a partial order, i.e. an order which is reflexive, anti-symmetric and transitive. So a poset, say S with this order, this can be viewed as a category. So this can be viewed as a category. So here let us call this category, denote this category by S. So this is a category S with objects as elements of S, and the set say, now the objects here are the elements, say, so we can write here home of xy, where x and y are the elements, I mean the objects in S. So this set is singleton if this set is singleton if x is less or equal to y, and empty otherwise. Now we have this definition. So a category so let C be a category. Then the category say C. Now here we write OP. By OP we mean opposite. Now the category is same as C. So there is, so the objects in C are same as the objects in C, I mean the objects in C. OP opposite is same as the objects in C, but the arrows are reversed. the category COP consists the same objects as C, but the arrows are reversed. But the arrows are reversed. I mean the morphisms are reversed. Similarly, we have a discrete category. A discrete category is one whose only morphisms are identities, whose only morphisms are identities. That is, if we have an object A in category C and an object B in category this category, I mean discrete category, then there are only these morphisms, I mean IA, IB. There are no morphisms from AB which connect A to B. I mean there are no connecting homomorphisms. Now in next lecture we are going to introduce the functors, and we'll discuss some important functors such as the covariant and contravariant.